a good time to start. We have Zihan Tan from U Chicago to talk about approximation algorithms for graph crossing number. Yeah.
Okay. Yeah. Thank you for the introduction. Thank you for having me here. So today I'll be talking about a subpolynomial approximation algorithm for graph crossing number on low degree graphs. And this is based on joint work with my advisor, Julia Chujoy from TTIC, and Zebedee Mahabadi, who was a previous research assistant professor at TTIC as well. So what is the crossing number problem? The input to this problem is a graph, and the goal is to compute the drawing of the graph in the plane with fewest crossings. Okay, so what do you mean by drawing? A drawing is a mapping that maps vertices of the graph into points in the plane and maps edges of the graph into curves connecting the corresponding endpoints. So a crossing is basically an intersection between a pair of curves. So for example, if the input graph is K4, a click on 4 vertices, then this is a drawing of the K4 into a plane. And this drawing have one crossing. This is the intersection between two images. Okay, so two things are forbidden. For example, first, we do not allow the image of an edge to pass the image of a vertex like this. We do not allow. Okay, and second, we do not allow three edges to cross the same point. So do not allow three curves to cross the same points. So basically, there's anything clever that you want to do to get around some crossing, it is not allowed. Okay, so this is the definition of a drawing, and the crossing number. Okay, so K4 we know is a planar graph. So if we draw it differently like this, then we do get a drawing of K4 into the plane with no crossing. Okay, so the crossing number of a graph is simply defined to be the minimum number of crossings in any drawing of G, and the goal is to compute the number and also a drawing achieving this number or approximately achieving this number. Okay, this is a graph crossing number problem. So it has a very long history. It was first introduced by Paul Tudor in the 1940s, and then has found various connections and applications in serial computer science. For example, graph algorithms, graph visualization, VLSI designs, and geometry, etc. And it has been extensively studied. So according to a bibliography maintained by Virtual, by the time of 2014, there are already 700 papers written on the subject. Okay? But despite all this effort, this problem is still poorly understood, especially from the perspective of approximation algorithm, which is the perspective that we're going to take today. Okay, and if you just think about it a little, some typical methods of designing approximation algorithms like LP or SDP simply does not work for this problem. So how do you characterize a crossing by a LP? Okay, it's not easy. So you basically need to work from first principles. And this is the most interesting problem. This is the interesting part of this problem that I like. Okay, so what we do know about the approximation algorithm for the crossing number, let's look at some previous work. So there are no non-trivial approximation algorithm on general graphs. Okay, so basically for general graph, no approximation algorithm is known. And the hardest result is only APX hard. Okay, so basically is a big gap there. But there is indeed one beautiful result about the crossing number, which is this crossing number inequality. It is by Aitai, Shivatao, Newborn, and Simirti, and independently by Layton. It says that if the number of edges is larger than 4 times the number of vertices, then the crossing number is of order at least m cubed over n squared. Okay, so it's a very beautiful result and has a very simple probabilistic proof. But the message that it conveys to us is that as long as the graph is relatively dense, then the crossing number has to be very high. Okay, but the most interesting part of this problem is really when the graph has a low crossing number, it has a very good drawing and depends on whether or not you can find it. So it makes sense, and it's also reasonable to look at a bounded degree graph in which the graph is not that dense. Okay, so for example, the graph has max degree bounded by a constant or max degree bounded by a slowly growing function of n. Okay, and this is indeed the research direction on this topic in the past 10 years. Okay, so now we will look at bounded degree graphs. And what are
Zihan, question for you. So in this regime, can one get a good approximation algorithm if m is bigger than 4n? Then it's like
no non-trivial approximation is known for general graph. If just say that graph is a little bit dense.
Okay.
No non-trivial. Yeah.
Awesome.
Mm-hmm. So this is only the lower. This lower bound is the only knowledge we have, and it is not tight. For example, a bounded degree expander, this is far from tight. Okay. So yeah, so let's look at some previous work on bounded degree graphs. So select the general case, the strongest hardness result is still only apex hard. Okay, and for a long time, the strongest approximation algorithm gets a O tilde n approximates. Okay, it comes from the celebrity paper by Layton and Rao, and in that paper they prove that there's an algorithm that finds n plus CRG joins. Okay, this translates into a O tilde n approximation. Okay, and there are later other papers that shave off some log factors. Okay, recently it was improved to n to the 0.9 by a sequence of two papers, first by Chuchoy, Makarchev, and Siridopoulos, the second one by Chuchoy. And later on, more recently, it was further improved to square root of n approximation by a sequence of other two papers by Kobayashi and Siridopoulos. Okay, so the currently square root of n is the best upper bound and the APX hard is best lower bound. And what our results are, we have two results on this in the past 3 years. The first result is a paper in 2020, is that we improve this approximation just by a little, which is from square root of n to the 0.488. Okay, but the more important contribution we believe in that work is that we provide a pathway, pave a pathway towards much better approximation. Okay, so this n to the 0.488 is really just a proof of concept. So what do we mean by that? All previous results, the O tilde n, the O tilde n to the 0.9, the square root of n, uses the same algorithmic framework. And it was proved that this framework cannot give better than square root of n approximation. So square root of n is the best that they can get using the framework. So they have already exhausted their power in that framework. And what we are doing is we used a modified framework to get around this barrier. Okay, so using this framework, we managed to reduce the crossing number on bounded degree graph problems to a related problem that seems easier. It is called the crossing number with rotation system problem. Okay, this is our first work. And the second work is that building on the framework on the first result, we further get a n to the little 1 approximation algorithm for this new problem, crossing number with rotation system. Okay, and this, together with the first result, gets a n to the little 1 approximation for the crossing number on bounded degree graphs. Okay, so currently the approximation ratio is improved from square root of n to n to the little 1, which is also the first subpolynomial approximation for this problem. Okay, so the remainder of this talk is divided into two parts. The first part I will talk about the first result. Mainly I will focus on the reduction part. Okay, so this is really a proof of concept, so no, not focus on that. And the second part, I will talk about the second result. So before I go to this two parts, maybe let's just first look at what the crossing number with rotation system problem is. Okay, so compared with the crossing number, it's just it's a modified version of the crossing number. So the input is not only a graph G, but also a graph G, and also for each vertex, a circular ordering, which is also called a rotation of all its incident edges. Okay, so for example, V1 is incident of these 4 edges, and we place a circular ordering, E1, E2, E3, E4 on them. Okay, and the output is a drawing of G that respects the circular ordering with fewest crossings. Okay, so basically these edges must enter this vertex in the drawing in this order. Okay, this is the crossing number with rotation system problem. Okay, so this is the problem, and we will go to the first and the second part later. So yeah, if you have questions, maybe it's a good time to ask right now. Okay, so yeah, so I will now dive into some technical parts, and feel free to stop me if anything is not clear at any moment. Okay, so first talk about part 1. It's a reduction from the crossing number problem to the crossing number with rotation system problem. Okay, so let's probably first look at the old framework used by all the previous algorithm that achieves provable guarantee for this problem. Okay, so so recall that all previous algorithm use the same framework, and it's also the framework that is used in practice. And it's a very simple framework. So the first step is compute a planarizing edge set of the graph. Here, a planarizing edge set is a set of edges in the graph whose removal leaves the remaining graph a planar graph. Okay, and the second step is just compute a drawing of the remaining graph in the planar way. Okay, and then we add this deleted edges back to the drawing. Okay, very simple framework. So if the graph is K5, we do know that it's not a planar graph, but deleting any edge leaves a planar graph. So if we draw a K5 minus 1 edge in a planar way like this, and we add the edges back, it gets a drawing of K5 with 1 crossing. This is just an implementation of this framework. Okay, so how do previous algorithms indeed use this framework? So let's look at each of the steps in more detail. Okay, first, it is not hard to observe that there exists a planarizing edge set of sides CRG. Okay, why is that? If we look at the optimal drawing of G, and for each crossing we delete 1 edge, then the remaining graph is planar. Okay, so this is basically deleting at most CRG edges and leave the remaining graph a planar one. So there exists a planarizing set of sides at most CRG. And on the other hand, the main result with Kobayashi and Serendipitous sequence of 2 papers design a polyglot approximation algorithm for computing the smallest planarizing edge set. So basically combined together, they give an algorithm that efficiently find an edge set, find a planarizing edge set with size approximately CRG. And this is basically the best that we can hope for the first step. So the first step is basically done. Okay. And in the previous paper by Joy, Makarchev, and Serendipitous, they showed that given an edge planary set, we can implement the second and the third step to compute the drawing with the number of crossings being at most E prime times CRG plus E prime. Okay, so this is if we just incorporate this E prime is bounded by CRG, then what we get is, what we can do is we can compute the drawing with CRG squared crossings. Okay, and this together with this N plus CRG, the very first result by Layton and Rao, get us a square root of N approximation. And this is basically exactly the way that the square root of N is achieved by the Kobayashi and Serendipitous paper.
Sorry, the hard part is step 3, adding the edges back to the drawing. Like, I assume you can do the planar drawing exactly.
Yeah, but we also need to choose wisely what planar drawing we really want. Yeah, because there are not 3 connected, so there are many. Yeah, so and this is the main result in the 2011 paper. Yeah. So yeah, but however, it has been proved that this square root of N approximation is the best we can get out of this framework, because it was proved by Joy, Madame Malhabadi that there exists a graph with crossing number K and a planarizing set with size K, such that any drawing that induces a planar drawing of the remaining graph has to contain at least K square crossings. So basically, the CRG square is the best we can hope for. And in this sense, square root of N is tight in this framework. Okay, so what we are doing is that we are modifying this framework a little to get rid of this CRG square bound. So what we do is we propose a new framework. Actually, it's a modified framework of the previous framework. The first, it has 4 steps instead of 3, and it's basically adding the second step. Okay, the first step is still the previous step, is computer edge planary set. And we are indeed just using the Kobayashi-Serendipitous algorithm. And after we get a E prime edge planary set, we allow ourselves to augment this set to a bigger edge planary set, such that the size is still approximate CRG, but the remaining graph has additional properties. We will specify later. Okay, and this properties is very useful in order to get around this CRG squared bound. Okay, and the third and fourth step in our framework is just similar to the same to the previous second and third step. Okay, the computer drawing of the remaining graph and add edge back. Also, it requires tricky ways to do it. So which planar drawing to choose and how to add edges back. So first question is, does this small modification even help? So why is adding this second step just helpful at all? And what we prove in the first paper is that it indeed helps. Okay, so what we can show is that we can augment the set E prime of edge planary set into a bigger set, such that there exists a drawing with approximately optimal number of crossings in which only edges of E double prime participate in the crossings. Okay. Originally, we want to delete a set of edges so the remaining graph is planar. And after we adding the edges back, every crossing evolves at least 1 edge of E prime. And now what we are requiring is that every crossing evolves 2 edges of E double prime, basically only evolve edges of E double prime. Okay, this is a stronger requirement, and it is indeed useful for us to get around this CRG cross barrier. And what we have shown in this first work is that after this algorithm for the main theorem, implementing the steps 3 and 4 is equivalent to solving an instance of crossing number with rotation system problem. Okay, and this is what we really mean by the reduction from crossing number to the crossing number with rotation system problem. Okay, so now I will sketch the proof of the main theorem. I will start with some motivation. Okay, so let's just look at the main theorem statement again. It says that there exists an algorithm that given a graph and an edge planarity set E prime with size approximately CRG, we can compute an augmented edge planarity set E double prime such that the size is still approximately CRG. And there exists a near optimal drawing with approximately optimal number of crossings in which only edges of E double prime participate in crossings. Okay, so one thing to note that is that here, I mean, for now, we do not know how to get this optimal drawing. As long if we can get it, we directly get a polynomial approximation for the whole problem. So we can only guarantee that the existence of near optimal drawing. Okay, for now. So how to prove this main theorem? We will be thinking of the graph G as original graph and the E prime as a set of edges that has been deleted from the graph. Okay, so the remaining graphs are possibly connected, but possibly disconnected. But if it is disconnected, we view it as a disjoint union of clusters. Okay, and these clusters, we will ensure that eventually it satisfies some properties, but currently it may not. So what we are doing is look at this cluster and further decompose it, recursively decompose it until it satisfies some clusters. So basically, we will start with E prime, and by deleting more edges, we put more edges of E double prime. Okay. Eventually, E double prime is just starting from E prime and adding edges recursive to it by decomposing the clusters recursively. So what are the good properties that we want to ensure about these clusters? There is a intuition theorem by previous work in the previous work by Chuchoy. It says that if a graph G contains a set of disjoint clusters that satisfy these 3 good properties, then there exists a near optimal drawing of G in which only edge of the edge of these clusters don't participate in net crosses. So basically, there's only intercluster edges that participate in crossings. Okay, so these 3 good properties are 3 vertex connectivity, strong planarity, and bounded well linkness. So what are they? So if this is a cluster, and 3 vertex connectivity means the cluster is 3 vertex connected. So basically, for every pair of vertex, there are 3 edge node disjoint passes connecting this pair of vertex. Okay, and strong planarity. So it is planar. It is a planar cluster. Okay, so strong planarity requires it is a planar cluster. So it has a 3 vertex connected planar cluster. So it has a unique planar drawing, and the strong planarity requires that all the boundary vertices, which are the vertices that are incident to edges that do not belong to these vertices. So basically the intercluster edges, the endpoint of this intercluster edges in this cluster, these orange vertices in this picture, they have to lie on the same face of the unique planar drawing of this cluster. Okay, so this is planar, this is 3 vertex connected, so it has a unique planar drawing. And these boundary vertices, they have to lie on the same face of this unique planar drawing. This is what we call strong planarity. Okay, and also boundary well linkness is basically saying that this boundary vertices, this orange vertices, they have to be well connected inside this cluster in some way. The definitions, the strict definition, I won't go into detail for now. Okay, so why is this intuition true? So why, if we have this clusters, then we can have a near optimal drawing in which this clusters do not participate in crossings? I will quickly sketch the proof. This is not the main focus of our talk today. But the idea is that we can massage the optimal drawing such that eventually all these green clusters are drawn away, are drawn separately and inside the disk, that are disjoint from each other. So assume that this is the optimal drawing of the graph. We are going to massage it. Okay, and how? So this green edges form a cluster, and they satisfy the 3 properties that we mentioned before, namely 3 vertex connected is a planar drawing with all boundary vertices lying on the outer face, which is the drawing on the right. And here is boundary vertices are A and B, okay, and they are well linked inside it. So we will first find a vertex C in the green cluster and a set of passes connecting the boundary vertices to C. And then we erase the green part from the whole drawing, and this is what it remains. And we now redraw its boundary edges, namely the blue edges, by starting with their original curves and then extending them along the paths that connecting A and B to C, which we have just found. And eventually they all lead to the correct location, in which we want them to end at C. Okay, and then we place a small disk around C. And then we put the unique planar drawing of the green part, which is the drawing on the right, back into the disk around C. And finally, we reconnect these blue curves to the boundary vertices A and B inside the disk like this. So we look at what is really happening inside the disk, and this is shown on the right. Okay, so observe that. Okay, so
Zihan, could you do that one more time? That went really
sorry,
fast.
I just want to briefly sketch. Sorry for being too quick.
No, that's all right.
Yeah, let's say this is the original optimal drawing, and this is the green part. We want to massage so that eventually the green part lies inside a small disk and is drawn in a planar way.
Perfect.
Okay. We start with the cluster and with this boundary vertices A and B. We know that it is boundary well linked. So this boundary vertices are well connected. So we can find a set of passes connecting them into a single vertex inside the cluster. And this is the passes we find. And we look at the image of these passes in the drawing. And this is the auxiliary curves that we will be using.
So you're saying that there is a vertex C such that all the boundary vertices have disjoint paths going to C?
Yes. Not disjoint, maybe low congestion passes.
Low congestion. Okay, perfect.
Mm-hmm. Partly because it is bounded degree.
Absolutely. Good point.
Yeah.
Good point.
So we erase the whole green part from the drawing for now, and we will insert it back. Okay, erase it for now, and we first draw the blue curve in a different way. So first, currently the blue curve are not ending at C, and we want it to end at C. So we extend the blue curve along this path, so that they all end at C. And we place a disk around C. We place the green drawing inside it and reconnect this curve.
Okay.
Yeah. So the proof that this series of operation does not increase the crossing number by too much is a little bit delicate, and we will not get into that, but this is the idea. Okay. So this is the algorithm. So if after processing these clusters, if we process every green cluster in this way, then the edges in the green cluster lies in a small disk, and they're no longer participating in any crossings. So, and these small disks are disjoint from each other. So finally, only the blue edges, which are the interclustered edges, participate in crossings. So this is the rough proof sketch of the intuition theorem. And the more important contribution is how do we actually achieve these three properties? So as long as we have these three properties, we'll basically get the first main result. So the idea is to start from the graph G minus E prime and look at its clusters. And currently they may not satisfy these properties, but we will further decompose them until they satisfy all these three properties. Okay. And we still want to ensure that the number of newly deleted edges is not too many. So we still want it to be approximately CRG. Okay, so let's look at this first three properties: three vertex connectivity, strong planarity, and bounded well linkness. The well linkness is somewhat easier to achieve because there are algorithms called well linked decompositions in previous work, and it can be shown that the number of edges that we additionally delete is not very many. Okay, so basically this boundary well linkness can be achieved by a classical algorithm called well linked decomposition. So let's look at the next one, strong planarity. This is something that is trickier to achieve. So recall that the strong planarity requires that in the unique drawing of this green cluster, all boundary vertices lie on the same face. So for example, this is a green cluster, and in the remaining graph, there are two connected components connecting to this green cluster via intercluster edges from, for example, the blue edges. And there are, for example, two connecting clusters, X and X prime, one connecting to the green from inside, one connecting to the green from outside. So there are 6 boundary vertices, 3 on the inside, 3 on the outside. And currently they do not lie on the same face. So in the unique planar drawing of the green, 3 of them lie on the inward face and 3 of them lie on the outer face. So this is not what we want. It is not good enough. And if we are going to make it happen, then we sort of have to delete one edge from each cycle. And afterwards, they now appear on the same face. But this is a little bit too costly because the number of cycles may be too many. So we might end up deleting too many edges. This is something that we cannot afford. So we have to relax this property a little bit. We have to replace it with a weaker property called the bridge property. So every cluster has a planar drawing in which every pair of boundary vertices that is connected in the remaining graph lie on the same face. Okay, so these three origin vertices, they are connected in the remaining graph. So they have to be lying on the same face. And these three are connected in the remaining graph, so they have to be lying on the same face. But all these six, they do not have to. Okay, this is sort of a relaxation property that we have to make, the sacrifice that we have to make. And now this cluster is just good enough because it automatically satisfies the property. So these three orange vertices is good, this good, and there's no requirement for this total of 6 vertices. But if, for example, there's another edge connecting x to x prime, making these 3 vertices also connected to these 3 vertices in the remaining graph, then in this case, we still have to delete one edge from each cycle. But now we are guaranteed that we can do so. Because if there is such an edge, then what we can prove is that the number of crossings in which this green cluster participated in any drawing has to be at least the number of cycles. So we are allowed to delete one edge per cycle. We can afford to do so. Okay, we can charge them to the crossing number. So this is the way we replace the second property with a weaker property and get around it, called bridge property. And it turns out that with some delicate operations, we can ensure these 2 properties together. Okay, so bridge property and boundary well linked property together. And for the third property, for the 3 vertex connectivity, it turns out we have to do similar sacrifice again. So it cannot be achieved immediately, but we have to get around it by replacing it with the weakened property, which is two vertex connectivity with some additional property. Okay, I won't get into the detail of that, but the idea is that we still need to relax it a bit, and we can eventually ensure all of them. Okay. So this is roughly the proof of the main theorem. I'm sort of ignoring several details in the ensure these properties, but the idea is we weaken the 2 of them and manage to get all of them, one original one and 2 weakened ones altogether. So this is the first part of the result. So it's the first main result. And let's look at where we are now. Okay, so we start with an edge planar ring set, and we augment it to be a bigger edge planar ring set. And eventually we get a bunch of clusters, which are the green clusters inside, drawn in this way. Okay, what we are promised is that there exists a near optimal drawing in which each of these green clusters are just drawn in this way. What we are doing is, what we need to do is to just complete the drawing by adding the images of these intercluster edges, the blue edges, back. Okay, and since these clusters are sort of good, basically they are planar, they are having a unique planar drawing, they have to be drawn in this way. And the fact that this planar drawing is unique defines a circular ordering on the all boundary vertices, and therefore it also defines a circular ordering on all the intercluster edges that is incident to this cluster. So basically, if we want to add the blue edges back, we can really think of this green parts as being contracted into a single vertex. And the blue vertices are the edges incident to these supernodes. And we are indeed placing a circular ordering determined by the unique planar drawing of the original green cluster. And this is basically reducing the problem into a crossing number with rotation system problem. Okay, now we are having rotations.
So Zihan,
yeah.
Because you guys don't quite achieve the 3 vertex connectivity, it isn't a unique drawing, is it? Or
yeah,
do you still maintain?
Yeah, so intuitively it is still a unique. So together with these so the graph is still 2 connected, and the 2 connected is basically the drawing is up to flip, right? And we have a locating the remaining graph procedure that really tells us which part of the remaining graph has to be drawn inside which phase. We indeed have this property, so it can be intuitively viewed as it is drawing in a unique way. So yeah, so this is the first part of the talk, and the basically the remaining part is to add this blue edges back, and it's really solving an instance of crossing number rotation system problem. Okay, the second part, we'll talk about our subpolynomial approximation for this crossing number rotation system problem. So let's look at this problem again. The input is not only the graph G, but also for each vertex, a circular ordering on all its incident edges. Okay, so here we actually place a circular ordering, but in fact, when we do allow that the flip is chosen arbitrarily. Okay, so basically the planar drawing is unique. It is also unique up to flip. So actually, when we find the drawing, it can just enter this in the circular order, in this clockwise order, and it also can enter it in the anti-clockwise order. Okay, but this is just some technical details that we will not put a focus on today. So the output is a drawing that respects all these orderings and have minimum number of crossings as possible. Okay, so what is previously known about this problem? In cubic graphs, so in the graphs where the max degree is bounded by 3, the crossing number with rotation system problem is just equivalent to the crossing number problem, because placing a circular ordering on 3 elements and still allowing flip is placing nothing at all. Okay, so the hardest result is still just APX hard from the previous result on crossing number on the cubic graphs. And the strongest approximation result is n to the 4 approximation, if the rotations are also given, if the flips are also given. This is by some previous work. So this n to the 4 seems a little bit weird, but in this crossing number with rotation system problems, we allow parallel edges. So m can be much larger than n. So n is number of vertices, m is the number of edges, so m can be significantly larger than n. So this n to the 4 is just non-trivial. So yes, a non-trivial algorithm. So what we proved in this work is that given an instance, we can compute the drawing with n to the little 1 times OPT plus EG crossings. Okay, EG is number of edges. So we allow ourselves to compare with number of edges. Okay, so recall what are the number of edges? It is the E double prime edges. It is the blue edges. It is the intercluster edges. So its size is approximately CRG. So here it's also approximately CRG. So it's okay that we compare ourselves to that number. Okay, so how the algorithm works, the framework is divide and conquer. So we will be dividing the graph into smaller graphs, smaller instances, and small enough instances such that we can compute some drawing on it in a trivial way. And this is the top-down divide step. And we will go bottom up, such that when we get a drawing of all the sub-instances, we combine them into a drawing of the instant that gave birth to them. Okay, so this is top-down divide and bottom-up combine step. This is the whole algorithm framework. And 3 things need to be guaranteed in order for this divide and conquer framework to work out. So first, when we divide a graph G into 3 sub-instances, G1, G2, and G3, the summation of the optimal number of crossings in these all sub-instances has to be bounded by the OPT of G. So it is not strictly less than, but bounded by OPT times some factor. Okay, so I'm ignoring that. And also, since we are both comparing ourselves to the number of edges and the OPT, we have to also let the number of edges, total number of edges be bounded as well. Okay, OPT bounded, edges bounded, and also there need to be an algorithm that combines the drawings of sub-instances to a drawing of the original instance that we give. Okay, and also the number of crossing cannot be exploded in this combined algorithm. So basically these 3 things, if we can ensure all of them, then basically the algorithm works. And we will try to ensure each of them. We will try to convey some idea in ensuring each of them. So let's first look at how the sub-instance should look like. Okay. So the immediate idea for constructing sub-instance is just to cut the graph into 2 pieces by deleting these orange edges and just get 2 edges and just let this G1, G2, the 2 remaining graph be 2 sub-instances. Okay, this is the first, the most natural approach. But this natural approach has a problem, which is in the combining part. Okay, so if we combine the drawing, then we might increase the number of crossings by too much. So specifically, if we have a drawing of G1 and have a drawing of G2, and we want to get a drawing of G, we have to add the orange edges back. And an orange edge is basically a curve connecting an endpoint on the left to an endpoint on the right. And in the worst case, it's possible that any single edge may just create a lot of crossings. In the worst case, that creates EG crossing. There are examples that trip them. So in the worst case, just we cannot afford to just adding any edge back creates just super big number of crossings. And this is probably currently the problem with this approach. So we cannot just let the subinstances look simply like this. What we propose is another approach that after decomposing the graph G into G1 and G2, we add a new vertex, a special vertex, both for G1 and for G2, and connect this like vertices incident to this cut edges to this special vertex by new edges, because it is purple edges. So the subinstances does not look like G1 and G2 on its own, but we add a special vertex to each of them. This is the graph that we will further recurse on. Okay, and the claim is this just gets around the previous problem that we talked about. And why is that? If we now have a drawing of the new subinstances G1, so the new subinstances include this red vertex, and we have a drawing of the new subinstance on right, then combining this drawing, what we can do is the following way. We look at the left drawing, we place a disk around the red image, around the image of the special vertex, and we place the whole drawing of the G2 instances back into the smaller disk around this disk, inside this disk. Here, we specifically allow that this purple curve touches this boundary. Okay, so this drawing all sync at the red point, but now we allow, we require it to touch the boundary in this way. And this can be achieved by carving out a small disk and viewing this small disk as the outer face. In this way, all this purple touches the outer boundary, but no longer sync at the same point. Okay, so we obtain a drawing this way. And then we reconnect this blue, this purple curves inside the annulus in this way. And this basically the entire curves now are the image of this deleted orange edges. Okay, so the claim is that we can indeed compose these two drawings in this way. And there are indeed crossings happening in this annulus region, right? And the sort of one technical part of this algorithm is that recall that we do have the freedom of defining the rotation on this special vertex and this special vertex. And we do it in a very careful way, such that when we really combining these drawings, there are either no crossing at all happening in this annulus, or the number of crossing happening in this annulus can be charged to the optimal, the CRG, the optimal solution. Okay, so this is sort of one technical part, but that I won't go into detail, but that basically shows that by adding this special node, we can get rid of the third worry. We can just achieve this. Only here we need to add a plus OPTG term. Okay, originally one that it's bounded, but here we do need this extra term. Okay, so what we are essentially doing is not decomposing.
Question about that. So do you, this could increase the degree at the red node, right? So do you like add in a complete binary tree or some kind, or?
Okay, so the crossing number with rotation system problem, the input graph no longer have bounded degree.
Okay.
Yeah, because we are contracting original pieces. So
perfect.
Yeah,
got it.
Yeah, so basically this is a way of designing subinstances in order to get around the composing part. So in fact, we will not be decomposing the graph into two parts and combine them together. We will be decomposing it into many parts and combining them together simultaneously. Okay, so in particular, we will create for each cluster a cluster-based instance and altogether a central-based instance in order to stick them together. Okay, I will not go into detail, but the idea is illustrated in the two cluster case. Okay, and this is called the basic disengagement. This is a subroutine that we will refer to later. Okay, so let's assume that we get around the third worry. We're no longer worried by the composing algorithm. Let's look at how do we get the first and the second property. Okay, so the first property is the summation of OPT is bounded by the OPT of the original graph. Okay, so if we do not have this special vertex and this special edges, then it is immediately true that this this holds, right? Because the original drawing just naturally gave a drawing of G1 and give a drawing of G2, such that the number of crossings in total is bounded. But what if we have the special vertices? The idea is still to use the drawing of G1, to use the drawing of G to get a drawing of G1. So extract a drawing of G1 from the original optimal drawing of G. Okay, so let's say we can find this edge disjoint passes connecting all the cut edges into a vertex on the right. Let's say we can find a red vertex and find these blue passes that are edge disjoint, connecting all these orange edges to the red. Okay, and then what we can claim is that now we can get a drawing of G1 out of the original drawing of G. Why? So the left part of G gives the drawing of G1, and now we view this red vertices, this red vertex as the image of this red vertex, and the original image of this entire passes as the new image of this purple edges. Okay, so basically we use this passes image to construct this edges image, if we can find this passes. Okay, so basically now we can extract a drawing of this G1 from the original drawing. And in the ideal case, they are edge disjoint, but the idea is using the pass to get the new edges, but in fact, we only need the low congestion. Okay, so edge disjoint routing gives perfect drawing, but low congestion routing still gives us cheap drawings. So it does not increase the number of crossing by too much. So for this to happen, we need to find these blue passes, and they require certain properties. And what are the properties that requires? Let's look at it in more detail. So look at the right part of the graph. What we are requiring is that all these boundary edges can be routed to a vertex inside it without creating too much of a congestion. Okay, so this is sort of a routing to a center criteria, the routing to a center requirement. Okay, so in terms of multi-commodity flow and multi-cut, this is implying routing all to all. So if we can route all to a center, then we can route all to all. Yeah, I'm not sure if it makes sense, but I'm just doing it at a high level in the multi-commodity flow way. And we do.
Zihan, is that because I can route to the center, and then from the center I can route back to the other?
Yeah, exactly.
Okay, good.
So
Thanks.
the flow, the flow has no congestion at all. Yeah. So, it's also the star is an expander. So yeah, but it's a sort of high level. But we do. What I want to say is we do have a characterization of this routing out to out property. It is called the well linkedness. Okay, so a cluster is called a well linkedness, or sometimes called boundary well linkedness. If for any partition of the cluster, if we look at the boundary edges lying on both sides, then the number of edges, which is the red edges that go across this cluster, has to be comparable with the number of boundary edges on the smaller sides. It has to be at least alpha times the minimum between this side boundary edges and this side boundary edges. Okay, this is called boundary well linkedness. So this is a characterization of this really routing out to all. So this is a cut property, but since we have low flow cut gap, this this cut property just also guarantees the flow property. Okay, this is still high level, but what I want to mean is that we do have this well linkedness characterizing this routing out to all. But is the inverse true? Is the converse true? Okay, so does this well linkedness, does route out to all also give us routing to a center property? Okay, and the answer is no, but in this work, we show it's almost. So, okay, what do we mean by almost? What we show is that for a well linkedness cluster, either we can find a random routing to a center, or we can say something else that is good with respect to this crossing number of this cluster. Okay, so either we can find a random routing to a center, which is a random set of passes, such that for each edge, the expected congestion square on this edge is bounded by n to the 1. Or we can say that, okay, the OPT of this cluster plus number of edges of this cluster is at least the number of boundary edges square. Okay, what do we mean by that? It is sort of the trouble created by this cluster can be charged to the cluster itself. Okay, so what is the trouble created? It is the new edges, the new vertices and the new edges. And what is the word that it can give us? It is basically every pair of edge may cross once. And how many crossing is that? Boundary edges squared. Okay, and what we are showing is that boundary edges squared is bounded by OPT plus EC. So the trouble created this cluster can be charged to the cluster itself. So either this criteria about OPT about the trouble created by this cluster can be said, or we can find a random routing to a center. Okay, so almost so the other direction is almost true, except that sometimes we will end up in this case. But in this case, since we are doing the crossing number problem, it is also a good thing for us because we can just extract this cluster out and recurse on its own. So in this problem, what we can show is indeed they are equivalent, since this thing is still a good thing to say about the cluster. So I would like to make two remarks about this theorem. This is sort of one of the main technical theorem about in our work. If we just want the congestion to be bounded, but not its expected congestion, then it's impossible to get, because some vertex just maybe the whole graph is still a bounded degree graph, and the number of boundary edges is too many. So some edge have to incur high congestion. So if we get rid of this expectation, then it's impossible. But if we get this expectation of congestion to be bounded by polylog n, then it's simple. And then it's simple because it's just automatically implied by the well-linkedness, but it is insufficient for our purpose. So A edge, if we have one crossing and A passes use this edge, B passes use this edge, eventually A may give birth to A times B crossings. So bounding it by congestion, bounding the congestion is not enough. We have to be bounding the congestion square, because A square plus B square can bound AB, but A and B cannot bound A. So just a very quick intuition. So yeah, probably hope they make just any sense. So expected congestion is not enough, and that's why we have to go to expecting congestion square. So basically, the main idea of this technical theorem is that, okay, routing to a center is equivalent.
So is the n to the little o of one losses essential, or could you get, is it possible that polylog is doable?
Yeah, so for this, we are not completely sure, but the current approach gets us n to the little one. It's a hierarchy of decomposition, and each layer we lose indeed polylog. Not sure if the hierarchy can be collapsed, but currently, yeah, we do not see a way to get around it. Yes, so okay, so this is basically saying that routing to a center is equivalent to the property of well-linkedness only in our problem. But okay, so recall that this set of passes give us a drawing of G1, the G1 new instance, but we also need a drawing of G2 new instances. So we also need a set of passes connecting these boundary vertices to something to some point in the left. Okay. So we basically want these boundary edges to be well connected both on the left and on the right. And this is something called doubly well-linkedness. Okay, so routing to a center is well-linkedness, but routing to a center inside and outside is doubly well-linkedness. While we have an algorithm that ensures well-linkedness, we do not have any algorithm that ensures doubly well-linkedness. And the second technical part of this paper is that, okay, what we show is that we do not really need this doubly well-linkedness. Well-linkedness suffice, but it comes as a cost, but it comes as a price. The price is the disengagement procedure has to be much more complicated. So we cannot do the previous basic disengagement, but we have to replace it with a much more complicated procedure called advanced disengagement. So what do we mean by that? Originally, the basic disengagement creates a cluster-based instance for each cluster. Basically, it's looking at each cluster and contracting the outside world into a single vertex. But now this does not suffice because we do not have doubly well-linkedness. So what we instead is to relax this procedure to get a more complicated procedure, which is we allow ourselves to decompose the remaining world into different parts and contracting each of the parts into a single vertex. Okay, so there's no longer one special vertex, but many special vertices. Okay, each instance is now constructed in this way, and composing them becomes much more complicated. But the idea is still like just composing them when they are just one special vertex for each instance. And I'll get to the detail of this part, but the idea is well-linkedness suffices, but it makes the disengagement, the combining joining part, much more complicated, but it still can be done. Okay, so the last property that we want to ensure is that the number of edges, the total number of edges is bounded. And also we, for this divide and conquer to work, we also need the number of edges decrease at each level by a factor of n to the little 1. And this n to the little 1 has to be larger than this red n to the little 1 in order for the whole divide and conquer to work. Okay, so this is achieved by applying minimum balance cut recursively to the graph. Okay, so a minimum balance cut is a balanced cut is a cut of a graph into two parts, such that each part contains at most 90% of edges of the original graph. Okay, and the minimum balance cut is a cut satisfying this condition and also minimizing the number of edges going across it. Okay, so it has been proved in previous work that the minimum balance cut is bounded by square root of OPT plus the max degree times the number of edges. Okay, it was proved by previous work. Actually, it was a corollary of the planar separator theorem. Okay, so OPT plus EG, it can be just enforcing a graph to be a planar type argument, and the square root of it is really the corollary of the planar separator theorem. Okay, so I have been proved that the mean balance cut have relatively small size if the OPT is, if either the max degree is bounded. Okay, so actually we cannot compute the mean balance cut, but we have to compute the approximate balance cut. Okay, so what we have in the from this previous result is that if the max degree is not crazy, okay, a crazy is just a one vertex take up almost all edges in the graph. Okay, so if the max degree is bounded by EG over n to the 1, then either OPT is EG square or mean balance cut is significantly less than the number of edges. Okay, just by looking at this inequality for 1 minute, okay, and get this either or type of argument. Okay, so this either OPT is very large is also a good thing for us. So what do we mean by OPT is larger than EG square over something? It basically means just forget about finding a good join. Arbitrary join is almost optimal. Okay, so every pair of edges, we can at least ensure they cross at most once. So any just non-stupid join give us EG square. So this is also something good. So we do not need to worry about this cluster at all anymore. Or we can get a mean balance cut that does not cut a lot of edges. Okay, and this is something good. So, but recall that this is, we do need one property, we do need one condition, is that the max degree is not crazy. Okay, so what algorithm that we are really doing is recursively apply the minimum balance cut until each cluster has small enough size. And then we apply well-linked decomposition of each cluster. And then we get well-linked clusters, and we can create subinstances using advanced disengagement. Okay, so the high-level overview of this part is that as long as the max degree is not crazy, what we can do is apply the minimum approximate minimum balance cut, and then well-linked decomposition to get small enough clusters, and then we use advanced disengagement to get subinstances. Okay, and if it does not happen, if the max degree is indeed crazy, we need a complete other type of arguments to get subinstances. Okay, so I will not go into that detail, but just a very high-level overview. We ask if these just crazy vertices are highly connected. If not so, then we cut along small cuts and get either small clusters or flower clusters. And then we use basic disengagement to get small clusters, and we use advanced disengagement to get subinstances. And if they are really highly connected, this means that we can find a set of many passes connecting two crazy nodes. And in this case, we just cannot use the previous disengagement. We will use a new type of disengagement called cycle-based disengagement and get subinstances. Okay, so this part, the bottom part, I don't think I have any time go into the detail of that. But the idea is that it's significantly different from the just no crazy vertex regime. Okay, so that summarizes the divide and conquer framework and also summarizes the algorithm. So this is basically the second part of the talk. And as a summary, we have a n to the little 1 approximation for the crossing number with rotation system, which combined with the first result get us a n to the little 1 approximation for the crossing number with rotation system problem. And for some future directions, maybe the most important one is still whether or not we can reduce this n to the little 1 to polylog, or whether or not we can prove stronger hardness result. Okay, and also what about the crossing number with rotation system problem? Okay, and that's all I'm going to say today. Thank you very much.
So I had one question more, which is that you started with E prime and then you augmented it to get E double prime.
Yes.
Is it conceivable that there's any advantage to like dropping edges from E prime to get a smaller set that, or those things are not very useful?
I see. So so what we want about E prime is that it is a planarizing set,
Right.
and the remaining cluster has good properties.
Right.
So as long as we do not explode the size by a lot, it's okay that we just start from arbitrary starting point and eventually just do not explode the size by a lot. So currently the augmenting step is just preserving the size by polylog factor. And we think of that as like enough for our purpose in the reduction. We have not thought of any backtracking edge sets.
Yeah, I mean, it would make your life easier because you have less edges to work with on this part. But on the other hand, how do you do it if there's no real idea of how to do it? Then I see your point.
So I have a question. You initially gave a lower bound, right? If m is at least 4n, then the crossing number is at least m cubed by n squared.
Yeah.
So it already shows like for at least 4n edges, the lower bound is like n, right? Omega n.
This is the crossing number inequality. So I mean, for the crossing number with rotation system, this does not hold because crossing number with rotation system, we are having multigraphs, and this holds for.
No. So I just meant for general graphs. This says if m is at least 4n, then the crossing number is omega n, right? And you already said that there is an algorithm which gives like crossing number plus n number of crossings, right? So it's like, isn't it like up to optimal up to order 1 for graphs with at least 4n edges?
See. Yeah, I suppose so.
Okay, so so the algorithms we are looking at are for m less than or equal to 4n edges, right?
I think so. Yeah. So. Yes. Yeah, I think so.
Okay. Yeah, thanks.
Awesome. Very nice. Bye-bye.
Yeah, thanks for the talk.